Using a force balance on a rectangular prism, demonstrate that the buoyant force is equal to the weight of the fluid displaced, and explain how this extends to an arbitrary shaped object. So we have the figure right here where we have a container. We're going to fill that container with some sort of fluid, and in that fluid lies a rectangular prism. In that rectangular prism, we'll have a specific density. In class, we made it have a density equal to the density of gold. In the fluid, we just made the fluid water. So in this case, fluid will have the density of water. And the rectangular prism will have a cross-sectional area of A. And so we need to find the buoyant force. So we're going to establish some variables. So the height of this entire prism is going to be big H. The depth from the top of the surface of the water to the top of the surface of the figure is going to be little h. And so you add these two variables together to get the depth from the top of the water to the bottom of the figure. That depth will be h plus big H. And so there's going to be a force pushing up, a force pushing down against the figure. And that will be the pressure force at the point H plus H. And that's going to be pushing up onto the bottom. And then on top, pressure force of H, or pressure force at the point little h, is going to be pushing on to the top of the figure. So if we take a look at this variable right here, the pressure force at H plus big H, the bottom of the figure, right? This is equivalent to the density of the fluid, because the fluid itself is pushing against the figure, acceleration due to gravity, and then times that by H plus big H, because we're at the bottom of the figure. That's our depth. And so we need to find the force. We need to find the force of both of these, and to find the buoyant force, we need to combine those two forces to find the total buoyant force. And so we're going to start with the bottom force. That bottom force will be pushing upwards. It's at a depth of h plus big H. And so we're going to use the same equation as pressure. That's the pressure at h plus big H. Recording? Yeah. And then times that by area. Because h plus big H times area, that gives us volume. And density times volume, that will give us mass. We have gravity right here. We multiply the mass times gravity, and this matches the force equation. F is equal to ma. So that is how we get our upwards force acting on the figure. Now we need to find the equation for the downwards force acting on the figure. That downwards force is at a depth of h, little h. And so same thing, density of the fluid, because the fluid is pushing against the figure, times that by acceleration due to gravity, and since it's at a height of little h, the height in this case will be little h, times this by the cross-sectional area. And so we can subtract these two values, these two equations. And so when we do that, we'll get the sum of forces is equal to rho of H2O, or the density of the fluid, times that acceleration due to gravity, times that by big H times A. And this right here is the buoyant force. Now we need to explain how it's equal to the weight of the fluid displaced. So to show off how that this is equal to the weight of the fluid displaced, remember that H times A this is equal to volume, and we multiply that volume times that by the density of the fluid, and in this case it's water. And so we'll get the mass of that fluid. In this case, it's going to be the mass times that, or it's going to be the mass of water in this case, times that by gravity. So the mass of the fluid multiplied by gravity will give us the weight of the fluid displaced. And so how can we extend this to just any arbitrary object? Let's do a little example real quick. I don't know, it's a person. But then to apply this is same principle. We could just divide this person into individual rectangular prisms. So there, rectangular prism, and we just divide any object to rectangular prism, and we find the buoyant force of each prism, and then we basically just add up all of the buoyant forces from all of the prisms we got, and we'll eventually get the buoyant force of whatever objects we want.